So what I'm going to do is just take you through very quickly and very generally the kinds of design, execution, analysis, presentation and interpretation errors that we find within research articles. And if you want more detail on this, then there's a great textbook by Altman, originally in 1991, although there is a second edition. It's in print still, and I suggest that this is a good start if you want more detail on these different types of errors. So if we go to the planning stage first, sorry, the design stage first, what are the common errors that we see in research design? The most common one, which is becoming more common, is that a study is not designed, but it just happens. And the reason why this is becoming more common is that we're seeing a rise in secondary analysis of data sets. And so when you design a study, you usually have a primary objective and an outcome variable, and then you would analyze for that objective. Whereas if you analyze sort of in a secondary sense, you're not using the outcome variables or the variables in the way that they are intended. And what may happen is that you have different sample sizes, different analysis techniques, etc., which then cloud the original objective of the research. And so what you need to do is when you're looking at research articles, always check that this is the primary analysis of, say, a trial or a case control study, and that, or if they've reported that it's a secondary analysis. So it's quite a different type of analysis for those two kinds of studies. Often we see that in case control or cross-sectional studies, for example, there are no concurrent controls, or if there are controls, they've not been randomized, which often leads to difficulty. It may be that the controls are not blinded, which means that the personnel involved in the study may introduce some kind of bias. It may be that the participants haven't been blinded appropriately. Sometimes we see that there's an inappropriate use of high-risk samples, maybe as the controls, but maybe as a study group, which means that you may be more likely to get a significant effect. Choice of inappropriate controls may be high risk, or they may be a particular selection of individuals. And most importantly, in the design stage, we often see an inadequate sample size, or no power calculation for the appropriate sample size, which means that we don't know whether, if it's a treatment, whether the treatment's effective or not, or whether the sample size was just too small. So those are some of the common errors that we see. Obviously there are many more, but it's just to give you an idea of some of the things that you should look for when reading through a research article in relation to the design. In terms of analysis, there are many problems with the analysis, particularly when we come to dental journals and medical journals. Often we see that the method of analysis that people use is not appropriate for the type of data that they have. And so what you should be understanding by now is that data comes in different types of forms, and those forms mean that you have to use particular statistical tests. And you need to check when you read through articles whether they report, for example, if it's normally distributed, and if it's not, that they've used particular tests. You find in research articles that data is paired, by which we mean that it's dependent, so the observations have come from the same person. So for example, in orthodontics, people look at teeth, and teeth are obviously related to one another because they come from someone's mouth. But when you look at the analysis, often in orthodontic journals, they analyse the teeth as though they're separate. But that's not appropriate because there's obviously a relationship between them. And I would say that this is the most common error. So using statistical tests and not taking into account that they will be related. The other very common one is to analyse not taking into account that there's ordered categories, i.e. they're not hierarchical. Treating multiple observations on one subject as independent, that comes back to the thing about not taking into account the relationship between different observations, and I'll come back to that in a minute. And often people tend to do lots of separate tests rather than one big test. And the problem with this is the more tests that you do, the more likely you are to get a significant result. So those are some of the common errors that we see in the analysis stage. In terms of interpretation, we see many different types of error. The first is that if a relationship is found between two things, say a relationship is found between age and oral health quality of life, that one has caused the other. Now the problem is that you cannot look at causation and assess cause and effect unless you do a randomized control trial. So any other type of design, you cannot say anything about cause and effect, one variable causing another. You can say a little bit more about causality in a longitudinal design, so you have a baseline and you look at what happens at some follow-up point, but you cannot say anything about cause and effect if you have a cross-sectional study. Often you find in the discussion sections of particular papers, they will talk about something causing something else, causation, when it's not appropriate to do so. Statistical significance, you may be aware now that if something is p less than 0.05, then it's seen as statistically significant. Often when you look very carefully within a research article, the authors may say that it's statistically significant if p equals 0.05 or is greater than 0.05, which is obviously not acceptable. It is slowly starting to change, but still there's not much reporting of confidence intervals within research articles. But actually what you should do is when you're reading through an article, the best kind of research study will report both the statistical significance, the p level, but also confidence intervals, because this tells you where the real difference lies. And the narrower the confidence interval, the more confident you can be in a result. Similarly, in terms of statistical significance, what you often find is that the reporting of statistical significance, the authors will then go on to talk about something being clinically significant if it's statistically significant. This is not the case. They are two very, very different things. So, for example, if you find that some treatment improves oral health quality of life on a measure, there may be a statistical difference between two groups. But if you just get a slight change in oral health quality of life, it may not mean anything. It may not be clinically relevant to an individual. So they are two very different things, and one should not be confused with the other. A similar point to my first, you cannot infer causality, cause and effect from cross-sectional data. Cross-sectional data is when you take all measures at one point in time. It's like a snapshot. You cannot say in relation to that kind of data that one variable has caused another. Okay, so those are some very quick overview of some of the problems that we see in different stages within the research design. Just to tongue-in-cheek, a joking way of thinking about this, Tricia Greenhay, who's a very well-known medical statistician, published an article a while ago now on 10 ways to cheat in statistical tests when writing up your research. And if you turn this on its head, it's a very good way of thinking about the problems that we see in research articles when we're reading them. So number one is throw all your data into a computer and report any significant relationship where p is less than 0.05. This is highly common, so what happens is, what you should do is you should have your objective and you should analyse to that objective. But what you tend to find is that people use all the data that they have and they just analyse absolutely everything, and the more you analyse, the more likely you are to get a statistically significant effect. We call this going on a fishing trip. If you have a longitudinal study, or if you have a trial of some kind and you have baseline, what you should always make sure is that the baseline, there's no difference between your two groups. If there is, then your follow-up is also going to show a difference, and so you will have a significant effect. If you have a baseline difference between your groups, you should always adjust for that difference. But often when you read research articles, people do not. For those of you who are doing the stats module, you'll have some understanding of what we mean by parametric and non-parametric tests. So these are different types of tests that we use for different types of data. When your data is normally distributed, you can use parametric tests. When it's not normally distributed, you cannot. But the problem with non-parametric tests is they're not very powerful, so people don't like to use them. And so what you find in a lot of research articles is that people do not report the normality because they don't want to use non-parametric tests. Another thing that's common is that dropouts and non-responders are not included in the analysis. Only those people who have complied with treatment are included in the analysis, which means that obviously this skews your results somewhat, because there may be a reason why those non-responders have dropped out and they need to be included in the analysis also. This comes back to my point about causation. So if you have a significant relationship, an R, a correlation statistic, then this means that there is a cause and effect relationship between those two variables. It does not. So sometimes you get people who produce what we call outliers, so very high or very low values, and they obviously skew your results when you're analysing. You should not take them out of your analysis, but often you see within research articles that they are taken out of the analysis, and so the sample size is reduced and includes only those people within a certain range. So often confidence intervals are not reported, as I've just said. One of the reasons why this is that they might overlap 0, and what you find then is that they're either left out or ignored if they're reported in interpreting the data. So in a trial, you obviously say before you begin how long the trial will be. This is not an error that we see so much now with the rise of the use of consort. But what you used to see in the literature was that a trial might be stopped after a certain length of period before the end of the trial because you've got a significant result. And so that significant result is reported as being the outcome of the trial when it shouldn't have been. Alternatively, the other thing we often see is that if a trial is meant to go on for 6 months, the analysis has been done and they're nearly significant, i.e. p equals 0.06, then the trial might be extended for another 2 or 3 weeks until that significant result is found. My personal favourite, and you see it a great deal in dental literature even today, is that if there's no significant result on the main analysis, then the authors will go back and find a subgroup of people, say Chinese women aged 52 to 61, and they will analyse just the data for that subgroup to get a significant result. And finally, number 10, if you're analysing the data and it doesn't give you the result that you want, you find some other statistical test to use, and that might give you the significant result that you want. So those are kind of tongue-in-cheek, jokey ways of looking at what's wrong with statistics in research articles. Things to think about when you're reading through different types of research articles.